All right, so today we're going to look at imaginary numbers. So imaginary numbers, we use the letter I when defining them, are just defined as the square root of -1. So what's kind of cool is imaginary numbers actually have some cool properties, and if we look at the higher powers of I, we can kind of see what I'm talking about. So if I take I and I square it, well, that's just going to be the square root of -1 squared. And we know that when we square a square root, we just get the radicand as a result. So I squared is -1. If we cube I cubed, well, that's I squared times another I. We know I squared is -1 times I. So that's just the opposite of I. So I cubed is the opposite of I. If we raise I to the 4th power, well, that's I cubed times I cubed is -I, right? The opposite of I times another I. So that's the opposite of I squared. Well, we know that I squared is -1. So that's the opposite of -1, which is +1. So I to the 4th, if you raise I to the 4th power, you get 1. If we look at I to the 5th, well, I to the 5th is I to the 4th times another I. And then I to the 4th is 1. 1 times I is just I. And so this right here, interestingly enough, is always going to be the pattern that this follows. If you raise I to any power, it's going to be one of these 4 values. It's either going to be I itself, right, the square root of -1. It's going to be -1, -I, or 1. Which is kind of cool. So this pattern just will continue. All right, so now I want to look at how do we simplify a radical with a negative in it, right? How do we simplify some of these imaginary numbers? So let's start with, for example, the square root of -18, let's say. So we know that this can be rewritten as the square root of -1 times the square root of 18. Well, we know that the square root of -1 is just I. And we know that we can actually simplify 18, right? The square root of 18, it's 9 times 2, and 9 is perfect square, it's 3 times 3. So we will get a 3 out, and this 2 will stay inside the radical. So it's I times 3 rad 2. Now, when we're writing this, we kind of treat I sort of like a variable. And so it's going to get stuck, it's going to move from here and get stuck in between the 3 and the radical. So this would be rewritten as 3I rad 2. All right, so let's take a look at how we can simplify some expressions that use imaginary numbers. But before we can do that, let's talk about the structure of imaginary numbers. So imaginary numbers have 2 parts or 2 components. They look like this. So this is the form of all imaginary numbers. A plus or minus b times I. So the a value here, that's what we call the real component. And then the bi is the imaginary component because it has this I, which we defined as being an imaginary number. So let's take a look at how we can evaluate or simplify some expressions that involve imaginary numbers. So let's try this. We want to simplify this expression. So 8 plus 6I minus 3 plus 4I. So these are 2 entirely unique imaginary numbers. So we have this imaginary number here, and then we have a separate imaginary number, and we're just subtracting the 2 of them. Now, what's pretty nice about this is we actually can treat this the same way that we would any other algebraic expression. We treat I sort of like as if it were a variable, and we treat 8 and 3 like constants. So with this value here, since the second expression, or the second imaginary number, is being subtracted, we can just think of that about this negative as being a -1 and getting distributed into both terms. So we can rewrite this without the parentheses and then do this this simplification. So the first one has like an imaginary 1 in front of it, so when we simplify that, it just stays 8 plus 6I. And then this negative gets distributed to everything, so it's minus 3, and then -1 times 4i is minus 4i. And then we just treat these as if they were variables and constants. So we combine like terms. So the 8 and 3, the real components combine. So 8 minus 3, that's 5. And then we combine our imaginary components. 6i minus 4i, which is positive 2i. So this expression simplifies to be 5 plus 2i. So this is an entirely new, unique imaginary number. So for the next example, I want to take a look at how we would multiply two imaginary numbers. So let's simplify this expression. So multiply the numbers 2 minus 3i and 4 plus 5i. 4 plus 5i. And so what's kind of cool is, just like with the last simplification process that we did, we're still going to treat this as if it were some binomial expression with variables. So the multiplication process for this is just like multiplying two binomial expressions using FOIL. So we still do the same thing, right? We multiply the first two, the outer two, the inner two, and then the last. So you just FOIL to multiply. So let's do that. So the first two, 2 times 4, that's 8. 2 times 5i, so that's plus 10i. The inner two, negative 3i times 4, so that's negative 12i. And then negative 3i times 5i, that's negative 15i squared. Now, if you remember back to the beginning of the video, right, we said that I squared is equal to negative 1. Negative 1. So this, right, is just negative 15 times negative 1. So we can then simplify this. It becomes 8 plus, so 10i minus 12i, that's a negative 2i. And then negative 15 times negative 1, that's a positive 15. Combine our like terms, so 8 plus 15, that's 23. So 23 and then minus 2i. So this is our product of these two imaginary numbers. All right, so next I want to look at how do we simplify a quotient of two imaginary numbers. So let's take a look at this example. 5 minus 2i divided by 3 plus 4i. Now, if you look at this expression, you might think to yourself, well, this actually looks like it's simplified. Doesn't look like there's any common factors that can be factored out and canceled. But unfortunately, we have this I here. And if you remember, we defined I to be the square root of negative 1. Well, that means we have a radical in our denominator. And thus, we have to actually rationalize our denominator here. So we're going to do that by multiplying by the conjugate of the denominator. So this conjugate is going to be 3 minus 4i, and then 3 minus 4i here. So we have to do this product in the numerator and then the product in the denominator to then work towards our simplified quotient. Okay, so let's do this multiplication. 5 times 3, that's 15. 5 times negative 4i, that's negative 20i. Negative 2i times 3, that's negative 6i. And then negative 2i times negative 4i, that's positive 8i squared. Okay, so that's the product in the numerator. Now let's do the product in the denominator. 3 times 3, that's 9. 3 times negative 4i, that's a negative 12i. 4i times 3, that's a positive 12i. And then 4i times a negative 4i, that's negative 16i squared. Now you can see that we have I squared and I squared here. So we know that those are both equal to negative 1. So this term up here is 8 times negative 1, so we can rewrite it as that. And then this is going to be negative 16 times negative 1. So we can rewrite it as this. And so if we want to simplify like terms, this is going to turn out to be negative 8. This is going to turn out to be positive 16. So now we can simplify our like terms and get our new quotient. So 15 minus 8, that's going to be 7. negative 20i minus 6i, that's minus 26i. And then in our denominator, we have 9 and a positive 16 here. So 9 plus 16 is 25. And then the negative 12i and the positive 12i actually cancel. So we get this as a result. But this isn't the best way to write our imaginary number. We want a real component and an imaginary component. So if you remember, anytime you have a binomial or a polynomial in a numerator and a single term in the denominator, we can actually break up the numerator all to be over the terms of our denominator. So we can rewrite this as 7 over 25 minus 26i over 25. And this is a better form because we have our real component and we have our imaginary component here. So this would be the simplified version of this original quotient. So like I said, the reason why we had to simplify this and multiply by the conjugate is because I is really a radical and we can't have radicals in the denominator, so we had to rationalize.